It's my pleasure to introduce Azarakhsh Malekian. She is a full professor at University of Toronto, and at the moment she's also a visiting research professor in Google. Azarakhsh is super expert. I know a lot of her papers in game theory, mechanism design, and especially network and data economics. And if you're interested, I'm very interested in data economics and data markets, and I read several papers of Azarakhsh. The papers are amazing. So Azarakhsh, thank you so much for being here with us today. So the stage is yours, and yeah, we are looking for it.
Okay, so today we are going to talk about the economics of data, and basically all of us are using data in our lives. How do we use it? You get a route to come here, you are using Google Map. The traffic when you're using it every day. You are just checking your social media to know what are the updates from your friends, everything. So in every aspect of our life, we see data. You use Netflix and you see like movies that are more relevant to your interests these days. And these are all enabled by data. So basically, these data-enabled algorithms are good for the users. And at the same time, this data also generates value for the companies, which help them to provide service to you. So basically, you are using the free service from Facebook, from the Google, because they are actually using your data in order to generate advertisement, better revenue from the advertisement, and that's how they are funded. So what we will expect is that this usage of data is going to grow, and there are many reasons. One of the reasons is basically we will have faster GPUs and better algorithms. As a result, we need more data to enable them to do better. This is like the food to the algorithms. And also, we will see every day more applications, and as a result, the users are also more willing to use them, which basically means that they're sharing their data. So more data will be available, and also it will be more useful because we have higher power, and also we are going to have better algorithms for the usage of this data. So what we would like to know today is that so far, most of this data exchange is something that is invisible to us. So basically, we are using these services. The maximum thing we are doing is like just acknowledging that they are using our data. And we are not like selling it to them. It's like we are for free, we are giving to them our data, and in exchange, we are getting the service. So now what we would like to know is that what would happen if we want to treat this amazing, high-quality commodity, which we call it the data, as a real commodity and exchange it for monetary transfers, allowing the users to own it and then see what would be the right mechanism for this exchange. And then after we talk about okay, so let's actually see how we should do the monetary exchange for the data, we will talk about what are the consisting still challenges that we need to address in order to mitigate these issues. So I will focus on the privacy considerations when I want to talk about monetary exchange for the data. Basically, we will talk about you have a data that you want to share, but the only concern at the moment that you have is your privacy. And we would talk about how the companies can actually exchange it for money. So with that in mind, I'm going to talk about two main topics that will be useful, just very high level to give you some background on the topic that we will talk about. And then I will jump into the main data market problem. So we are going to use game theory and mechanism design. And the reason is that basically similar to any other market, when you are facing basically strategic agents, which are us, you need to actually think of it as a game instead of an optimization. And I'm going to also talk about a little bit just what would be the definition of this privacy thing that I'm referring to. And the reason is that while everyone thinks that they know what is their privacy, there are many different definitions for privacy. and some of them are more standard than the other ones. And we would like to first formalize what would be the concepts. Well, how would we define this concept before we jump into the topic? Okay. So let's start with the question, the main question that we will talk about is that we are going to talk about a data acquisition problem. So basically, you will have a company, for example, it's like a drug company, it's a pharmaceutical, and they would like to get the data from the users in order to figure out whether the drug is more efficacious, it's better for the consumers or not. They want to gather that data, but at the same time, they want to compensate the users for their privacy loss. So we would like to know how we should do this data acquisition problem. And then we would talk about if we are just looking at this problem, whether it would be still fine at the end of the day, or there will be still issues that we need to address in future. So let's start with some background on the game theory and mechanism design. So I will start by trying to define what is the difference between the optimization and game theory. So I think everyone in this audience is familiar with the optimization. So basically, you have some objective in mind that you want to maximize or minimize subject to a bunch of constraints. So usually, you define the optimization like this, okay? So if I want to say what would be the difference with the game theory here, the difference would be the following. So at least, so you have a global optimizer in the optimization that will decide about this vector A, right, when you want to do the optimization. Now, for the game theory, what will happen is that this AIs in the vector A, each entity AI belongs to one of the agents. And these agents are strategic, and they're deciding by themselves what they want to set as AI. Okay? So they have also some utility for themselves. And as a result, each of them separately decide about their AI. And while from the designer perspective, you have a global goal in mind, you cannot force them to do that. So that would be the difference between the game theory and optimization. So in particular, in the mechanism design and game theory, basically you have a designer who has a social choice in mind that wants to, for example, optimize. And then for this optimization, he's facing a bunch of strategic agents, and he wants to direct them toward the outcome that they want. So basically, he's designing this mechanism in a way that they will act as he wishes. Thanks. OK, so let me formally define the game theory. So basically, you have a set of strategic agents. You have n agents, and each agent is they're interacting with each other. Each agent is taking an action. I'm denoting the action of each agent by AI, which is belonging to a set mathcal of AI. And this is the action of an individual. Yes. And the set of all actions of the agents together, I'm going to denote it by boldface A. So now an agent receives a payoff, which we basically denote it by UI of A. And that would be the utility of that individual. So basically, in the game theory, each of you have your own utility based on the action that you will take as well as the other people will take. Okay? So it will be a function of all of the actions of everyone. And you are rational, so you want to maximize your own utility. So basically, you are going to decide about this AI in a way that it will maximize your own utility. Now, since agents are strategic, they are going to try their best to do their best action. However, note that when I'm defining this utility for individual I, it's not just a function of your own action, but also depends on what others are going to do, right? So as a result, we have to define some notion to understand exactly how you would act, right? Basically, it's like a stable point, right? Or in other words, it will be an equilibrium. So basically, you are going to best respond to what others are going to do, predicting what they are going to do, because all of you are going to probably act simultaneously, right? So that would be the equilibrium notion that we see here in the game theory. And we are going to focus on static games. So the word static refers to the fact that in this game that you are playing, all agents are supposed to act simultaneously. So all of them together will take an action. So as a result, when you are taking action, you don't see the others' actions. You cannot respond to the fixed actions of the others. And it's a simultaneous move game. The opposite of the static game is a dynamic game where you will define turns for the users, and they can see what happened so far, and based on that, they can react. A concept that is very standard in the game theory is to define the action of each individual by subscript I, and to define the vector of the actions of everyone else by A minus I. So basically, whenever I refer to something minus I means like the actions or the types of everyone except the individual I. So now we are ready to define the notion of the equilibrium. So note that we are going to be in the static setting, meaning that everyone acts simultaneously. And then we would like to know how we can formally define the best response of an individual to other people's action when they are playing this game. So there will be different equilibrium solution concepts that are used in game theory based on how strong you can define that notion. So one of the strongest equilibriums, and actually if you have such equilibrium, one of the best equilibrium is the dominant strategy Nash equilibrium. What does it mean? Basically, if you can find an action for an individual that is best response to the actions of the others, no matter what that is. In particular, so this action is like the best of all worlds, right? No matter what others are doing, compared to your other actions, this will give you weakly higher utility. So as a result, this would be a dominant strategy for you to take. And we will call a vector of actions dominant strategy Nash equilibrium if for every individual you can find such action. Of course, based on the definition that I'm giving you, you can see that this is a very strong notion, and it's not necessarily the case that you can always find such equilibrium in the games. So that would suggest that probably we need to also look at some more friendly equilibrium, which is the pure strategy Nash equilibrium. So while this is not very weak, this is one of the most common equilibrium notions that is used. So what is the definition of the pure strategy Nash equilibrium? So basically, we are saying that an action AI for agent I is in the pure strategy Nash equilibrium if, assuming that everyone else is playing in the equilibrium, the action AI that you take is giving you a weakly higher utility compared to any other action that you take. So the difference between these two definitions is the following term. In particular, in the dominant strategy Nash equilibrium, your action should give you a weakly higher utility in response to all other possible actions of the others, okay? Whether it's the equilibrium or not, okay? However, in the pure strategy Nash equilibrium, it suffices that it is a best response to the equilibrium strategies of the others. Okay, so assuming that everyone else is in the equilibrium, this action is giving you a weakly higher equilibrium. And as you can see, in this situation, you will be in a stable point. So if you get to the vector that everybody is playing their pure strategy Nash strategy, no one wants to change their action, right? Because they are getting like the fixing everybody else's actions. You do not want to deviate, right? Unilaterally deviate. So as a result, it will be stable. Okay. So while this is weaker than the dominant strategy Nash equilibrium, it's still, this is not very weak, and in fact, there are many situations where you will not have any equilibrium, any pure strategy Nash equilibrium. Okay, so let's actually look at some examples here. So the first example that we are going to talk about is the prisoner's dilemma. So in the prisoner's dilemma, you have two prisoners that they can either confess, or in other words, they can stay silent, or they can confess, confess and say that the other one is doing the right action. So the utilities that you will get, as you can see, are given in the table above. So basically, if both of them are staying silent, both of them are getting -1. If both of them testify, both of them will get -2. And if one of them is silent and the other one testified, the one that's testifying is getting 0, which is higher than any other action. But for the silent one, they will get basically a -3. Okay? So can you guys find any equilibrium? So what strategies do you think will be an equilibrium here? Both testify, exactly. So both testify here. While it's not giving you like a very good utility, this is a pure strategy Nash equilibrium, right? Why? Because if both of you, if the other person is testifying, right? So suppose that, for example, individual 1 is testifying. Now we would like to know whether individual 2 will decide to testify or not. So basically, we will be in this row. And if the individual 2 stays silent, his utility from -2 becomes -3, which is not good, right? So as a result, you do not want to deviate. You can do the same thing for the agent 1. Basically, if agent 2 is testifying, then if you are, instead of testifying, you go silent, your utility becomes -3, which is not good, right? Now, okay, it's a pure strategy Nash equilibrium. Do you think that it is anything else based on the definitions that we had so far? Let's see. So actually, let's check. Can we find, let's check whether we have a dominant strategy for example, individual 1. So let's actually look at individual 1. So this is individual 1. It has 2 actions of being silent or testify. Okay? So if individual 2 is taking the action silent, what will happen? If the agent 2 is silent, we are in this column, and basically, you still prefer to testify, right? If individual 2 also testifies, you still prefer to testify, right? So it seems from the perspective of individual A, you have a dominant strategy. You can try this again, and from the perspective of individual B, also you have a dominant strategy. So in other words, this testify is a pure, it's pure strategy Nash, and also it's a dominant strategy equilibrium, right? So, so this game has both of them, which is good. Now let's actually look at the following game. Suppose that we are looking at the penalty kick. You have a kicker and a goalie. And of course, it's like a zero-sum game, right? Basically, if you look at the sum of the utilities of the two parties, the sum will be 0, right? So it's a zero-sum game. Now, we would like to know whether we can find a pure strategy Nash equilibrium here. So do you think that we have a pure strategy Nash equilibrium here? I mean, like if you think about the game, the football game, do they have a Nash equilibrium that they play? No. What do they do? How do they act? Randomize, exactly. So in fact, if you double check every entry, basically you can go over all of these entries by one, which basically are representing a pair of actions. You can verify that neither of them is a pure strategy Nash equilibrium. In other words, in every cell you are, one of the players wants to deviate. Okay, so one of the players wants to unilaterally deviate, which means that it doesn't have pure strategy Nash equilibrium. And as you suggested, and as the goalie and the kicker is playing, the equilibrium here is to play a mixed equilibrium, a mixed strategy. So basically, you will take each action with probability 1/2. Okay? This is another sort of equilibrium that is called the mixed Nash equilibrium. It's actually a very good definition, because in many situations where you can, while it's very, very hard to show the existence of a pure strategy equilibrium, mixed Nash is much, much easier to have. And in fact, if you have a finite game, you always will have a mixed Nash equilibrium. So if I want to be more formal, basically, a vector of mixed strategies is a Nash equilibrium if your utility, assuming that everyone else is playing in the mixed equilibrium strategy of themselves, will be maximized if you are playing your current mixed strategy that you are putting. So it's very similar to the pure, except that you allow the randomization here. So these are some basic definitions that we have for the equilibrium notions that will be used. And now let's actually get to the mechanism design. So far, what I was assuming was that everyone, while they're playing simultaneously together, they exactly know what is the utility of others, right? So basically, I know if you play as the goalie, how much would be your utility if if I kick on right and you stay on left, right? We know exactly what would be the utilities. This is called perfect information environment. So you basically know everything about the game. You know your utility of everyone exactly. So basically, if I fix the actions of everyone, you know what would be their utility. This is a perfect information. However, in many cases, the utility of an individual also depends on the information that that individual privately have. Okay. So, for example, if you see a person who is buying an art, right, like a painting. You know how much they paid, right? But you don't know exactly how much they valued that art, painting, right? That part is a private information. You know that if you knew that value, your utility would be that value minus the payment, right? But still, you don't know that value. So the utility function structure is known, but the type of that person, which is that value, is not known to you, right? So sometimes some parts of the informations are not known, not visible to the other agents. So we refer to this as an agent's type. So people have different types. So for example, you could be a person who has a high value for a painting or a low value for a painting. This would be your type. And we are going to denote the type of individuals by tau. Now, when we want to define a utility of an individual, it will depend on everybody's actions as well as the type of you, right? So for your own utility, you care about what others are taking, what are the other actions they are taking, and also what is exactly your type, right? So basically, for example, if you go to an art gallery, if you want to know what would be, and suppose that everyone is submitting a bid for the painting, so the bids that the people are submitting are going to be their actions, and then you have a private value that is, for example, V. The utility that you will get is what? It depends on what is your real value, and also what is the bids of the others. In other words, whether you will be a winner or not based on the submitted bids. And then, as a result, you will get the painting, and also, like, if you get the painting, how much it value you, which is basically your type. So in this case, your utility will depend on both the types and also the actions. And when we do not have a perfect information, when this type information is private, we need to make some assumption about how the other peoples are going to act, right? Because we would like to predict their actions and then respond to that, right? So what we are going to do is that it's a common approach to consider a Bayesian approach. So basically, you will assume that you know what would be the distribution of the types of the other people. So you know that the other types are not known, it's private to them, but you know that it is coming from a distribution, which is a public knowledge to you and also other players in the game. Okay? So based on this, we also will define the Bayes-Nash equilibrium. So a pure strategy for player I, bi, is a function that maps their types to actions. And then since the agent only see their own type tau I, they need to form a belief about the other individual types, right? Because when I want to know what would be the action of the others, it depends on their type. You will take your action based on your type, right? And you are going to predict. So you are going to make an expectation, and that would be based on the distributional information that you will have about, like, what would be the, using the Bayesian information, you would like to form a belief about what would be the chance that each person will have a specific type. And then based on that, what would be the predicted action for that type? And then as a result, what would be your utility? So that's how you will calculate your utility function. So the expected utility of an individual I, given the strategy function above, will be what? So basically, it would be the utility of I if you are taking the action of bi of tau I, and you're going to getting expected over the potential types of the other people, where this type is coming from a distribution P, which you condition it on the only information that you have, which is your type. So for example, if the types are independent from each other, then you can actually ignore this. It would be just tau minus I is coming from the, for example, uniform distribution, okay? If they have correlation, then you need to actually keep your type in the picture. For our purposes, you can actually ignore this conditional part, okay? So we are going to deal with the independent draws. So basically, your utility, when you want to calculate what would be your utility for taking the action of bi of tau I, you need to know what would be the action of the other people. And the action of the other people, since it depends on their types, you need to get an expected over those, right? So you will get what will be your expected utility when other people's types are coming from the distribution P, okay? And using that, we can define the Bayes-Nash equilibrium. So now Bayes-Nash equilibrium is very similar to the other Nash equilibrium definitions that we have, except that you will have an expectation here. So the type matters as well. And since we don't know exactly what are the types of the other people, basically your action should maximize your utility in response to the actions of the others. But since it's a simultaneous move game, you are going to predict what would be their actions. Since you don't know their type, you need to get an expectation over those, right? So this best response should be maximizing the expected utility that you will have in response to the other people's actions, okay? So that would be the Bayes-Nash equilibrium, and this is the common equilibrium notion that is used in the mechanism design, Bayesian mechanism design, where you would like to, for example, sell items, or, for example, for the auction design, okay? Okay, so basically, when we are dealing with the Bayesian mechanism design, here we are, it's very similar to the painting auction question. So people, users have, for example, private costs or private values for an item. And as a designer, as a mechanism designer, you would like to somehow maximize some social choice function. For example, if you are the owner of the painter, your social choice function is you would like to maximize the profit you would earn. Okay? If you are from the perspective of a social planner, perhaps you would like to find a way of gathering this information so that you would maximize the total surplus generated from the outcome that you will have. And let me give you an example. So you have an auction for the painting to maximize profit. Here, the agent's type, as we said, represent their valuation for a piece of art. The strategies will be their bid. They will submit a bid to, so that based on the bids, it will be defined who will be the winner. And the mechanism designer goal is to sell the item for the highest possible price or the highest possible payment based on the bids. So we are going to, again, the setting that we are going to deal with is the simplest setting in mechanism design, which we call it the single-dimensional setting. What does it mean? Basically, each user can, you can get their utility if they give you just one number, one scalar. Okay? That would be a one-dimensional mechanism design. When you move from one-dimensional mechanism design is very well studied and very well understood. When you move from one-dimensional to just two-dimensional, all of a sudden, the problems becomes much harder. And basically, you can say that if you are in a Bayesian setting, more or less, not much is known. So not much can be done. Okay. We are going to focus on the simple single-dimensional setting, which would actually suffice for the purpose of our privacy consideration. So basically, in the single-dimensional environment, when you are dealing with the mechanism, based on the submitted bids, you are going to decide about allocations. For example, if you are thinking about a painting, from here on, the allocation I will denote it by xi of b, which basically says, given the bid vectors, who will get the item? Okay, so for example, it could be that I will see the bids and I will allocate it to the person with the highest bid, or I will get the bids and I will allocate it randomly to one of the bids, or I will get the bid and I will allocate it to the randomly between the top two bids. I can do any of these sort of allocation. So the allocation is based on this bid vector, how you would give it to the people. The payment will be that, okay, now I'm giving you the painting, and I will charge you, based on the bids that you submitted, some amount. For example, the very famous English auction, or the second price auction, is the following. It will say, submit your bids. I will allocate to the person with the highest bid. So whoever has the highest bid will get the item. How much would they pay? They pay the highest bid among the rest of the people. Okay, so you will not pay your own bid, but the highest bid among the rest of the people. This is called the second price auction. And as a result, your payment is just a function of the vector of submitted bids. Now, what would be your utility? Your utility would be your real type, your real value that you have for the item, multiplied by the allocation that you will get for the bids that you submitted. Note that the designer doesn't know your value, only sees the bid. So based on the bids, I will decide, and then your utility will be your value times the allocation that you will get based on the bid, minus the payment that you will pay me, again, based on the bid, because from the auctioneer's perspective, the only thing that they can see is just the bids. They do not see the real values. It's a private information. Okay, and the utility of the, for example, if you want to maximize the profit, the utility of the designer will be just the summation of the payments that you will get from all individuals together. So depending on how the designer picks the allocation and the payment function, it may have different equilibria. So when you want to design this mechanism, of course, there are many different sort of mechanism that comes to mind, and it has a very huge space. You want to maximize your TI of B subject to nothing, basically, right? So when they wanted to approach this problem, they tried to actually limit the space that they need to search in. Or in other words, they wanted to see that, are there any smaller classes in the mechanism design that would be sufficient for me to focus on, and it would be without loss, okay? So that is motivating the revelation principle. So the revelation principle states the following. It says that if you have any mechanism with a good equilibrium, then you can find another mechanism which would be equivalent to this mechanism in terms of the profit or the revenue that it will generate. And at the same time, the best equilibrium strategy for everyone is to bid truthfully, or in other words, to really tell me what is your value. Okay? So basically, for any mechanism, for most of the reasonable equilibriums, if I have a mechanism, I can reduce it to the class of mechanism that the best strategy for each individual is to tell the truth. Can anybody tell me how? So note that you are the mechanism designer, right? You are given a mechanism here. It's a black box mechanism which has some allocation and some payment, right? Given the bid functions, right? And suppose that the bid function is just a function of your type, okay? So now you are the designer, so just add a proxy. What you will do is that you will tell the user that, okay, tell me the truth. What I will do is that first I will apply the proxy, the bid function, on your type. Then I will enter that to to the black box, and will get what would be the allocated item, how much would be the allocation, and how much would be the payment, right? So as a result, now in this bigger box, the entry will be the true type. Inside the box, what I will do is that first I will apply the bid function on it, and then I will fit it to the black box, right? As the designer, right? So as a result, your best strategy here is to tell the truth, right? So this is the reduction that you are suggesting, right? So as a result, revelation principle, while very simple, it actually helps you a lot in finding the best mechanism, because you can just focus on the mechanisms that the best strategy for everyone is to tell the truth, right? And then as a result, you can also play with the distribution information there, because the distribution of the values stays the same as the distribution of the bits, and that would be helpful when you are calculating your, for example, optimal mechanism. So the mechanism, so for the revelation principle, there is a requirement that the seller, the designer, can commit, right? And the reason is that I was telling you that I'm telling the buyer I'm going to apply this bid function first if you tell me the truth, right? So it should be a commitment ahead of time, and to ensuring that when the buyer really reveals their type, they're not going to manipulate and go back to the original mechanism. So there should be a commitment power here. So given the revelation principle, from here on, we are going to focus on the mechanism that the best strategy for individuals are truth-telling, or in other words, they call it the incentive-compatible mechanism. And here is the nice result. So when we are in the single-dimensional setting, when you want to find what would be a Bayesian incentive-compatible mechanism, there is a very nice if and only if characterization for the incentive-compatible mechanisms, which basically says that if you have an incentive-compatible mechanism, if you have a truthful mechanism, first of all, your allocation rule should be monotone in your bids. So in other words, if your bid is higher, then the chance of being allocated to should be also higher. Okay? So this is the first necessary condition. And the second condition is called the payment identity or payment characterization, which basically tells you the expected payment that you will have if your type is BI would be equal to can be written in terms of just your allocation. So it would be basically the value that you will get for the current allocation minus the integral of the allocations from 0 to the current bid. Okay? So as you can see now, the payment completely can be written closed form in terms of the allocation. There is no more T here. As you can see, only X is showing up. And this is really nice. Note that as a mechanism designer, you are deciding about two things, allocation and payment. Now, we said that if you have revelation principle, you can focus only on incentive compatible mechanisms. And then here we are saying that if your mechanism is incentive compatible, then in fact that payment can be written in terms of allocation. So basically your optimization at the end of the day becomes just an optimization in terms of just one thing, one function, which is just the allocation function, which is really nice. And to see how we are deriving this payment identity, it's very simple to see. So basically, let's see what is this incentive compatibility means. So recall, we said that if your mechanism is incentive compatible, it is in equilibrium for you to tell the truth, right? So in other words, basically, if you tell the truth, your utility will be bought. Your utility will be your type multiplied by the allocation for that type minus the payment for that type. And if this is an equilibrium, your utility for this bit function that you submitted should be higher than any other bit. So it should be greater or equal to the value that you will get if you bid any other thing such as B. So Ti is your type multiplied by the allocation for any other bit minus the payment that you would get for any other bit, right? Or in other words, basically, if you look at this part, you are trying to maximize this function and as a function of B. So you would like to know for what value of B this would be maximized, and you would like that B to be your real type, okay? So when you get the first order condition, you will basically exactly get that clean payment characterization directly. And there is no magic there, okay? Okay, so this is what we wanted to know about a mechanism design. We will get back to this mechanism design when we are doing the data acquisition, but I just wanted to give you some background on how mechanism design, how people are designing mechanism. The second part that I'm going to talk about is also the privacy, because we said that we would like to acquire data from the people, and the people care about their privacy. So what is privacy? Like, how do you... I'm talking about numbers. It's not as if I feel upset about my privacy being violated. It should have a numerical value on it as well, right? So let's try to quantify and define measures for the privacy. So the issue is the habit. I have the habit of clicking, and then I figure that it doesn't work. Yes?
I have a question. So if we care about not expected of our profit over rivals type, but in, let's say, the tail, some risk considerations, can we still talk about incentive compatibility? So it's not just expected operator, but CVAR or something like that.
So here in this IC constraint, you're saying how to change it? So you're saying...
So instead of expected operator over the type of the rivals, we talk about our profit in the worst tail, for example.
Oh, I see. So instead of the... so as long as you can write it like in a closed form like this, still the first order condition should hold, right? Because you're maximizing and trying to... The monotonicity might change, but still like the first order condition, as long as you can just summarize it into like one sort of expectation term, not exactly like the expectation that we have here, but a different sort of function of that, then the first order condition should hold, right? And yeah, so then you can, but it will have a different meaning, right? So, and then when it has a different meaning, the question is when you want to put it back in the objective function, whether it will have the same definition. So definitely you can simplify the incentive compatibility constraint, but then when you want to define the profit, it would not be as straightforward as this one, right? Because here, when I have the Ti of B, I can just directly put it in the objective function, right? But then if I make it different definitions for that, I need to update the definition of the objective function. Okay, so Let's now go to the privacy. Okay. So one of the most famous definitions that is used for defining a measure for privacy is called the differential privacy. That probably you have heard the name. And differential privacy is a very strong, robust notion. It's a worst case notion. And it's basically the one that is used by Apple, by Google, and also by the census. So it's a strong notion. So let's actually see how they define the differential privacy. So based on the classical definition of the differential privacy, we are saying that an outcome of an algorithm A is epsilon centrally differential private if the following holds. Suppose that you take an action, you change the data of one user. So here, for example, you change the data of user I from theta I to theta prime I, and keep all the other data points the same, and feed it to the algorithm. The distribution of the outcome of this algorithm, which is potentially a randomized algorithm, should not change much. In other words, from the outcome that I will see from the algorithm, I shouldn't be able to detect that you changed the type of this agent much, okay? So that would be the basic definition. Now, let me ask you the following question. With this definition, if epsilon is smaller, do you think it would be more private or not? Let's put epsilon 0. What does it mean? If epsilon is 0, basically this is 1, right? So basically it says that these two distributions should be basically exactly the same, right? Because one more time, I can also change theta prime to theta, and still this should hold, right? So as a result, basically, if epsilon is 0, it says that this distribution should stay unchanged if I change the data point of one person. Right? And it's basically very private, right? So when epsilon is small, user's data has less impact on the input of the algorithm, implying lower privacy loss. Okay? So from here on, I'm going to refer to the epsilon I as the privacy loss for this exact reason. Okay? Now, this definition has some issues. So basically here, what we're talking about is we say that, okay, if I change my data, how much the outcome of the algorithm will change, okay? Now, think about, for example, the following example. Suppose that you have two people. One of them is very privacy conscious, and the other one is not at all conscious. And they, like the sister doesn't want to share anything about their DNA, the brother doesn't care, okay? So 123andMe, the brother would participate, and the sister doesn't want to participate, okay? Now, when they give it to the algorithm, there will be it will be a function of just the brother, because the sister says that, okay, I don't want to share my data with you, okay? Now, do you think that this would be, from the perspective of the sister, do you think that there would be any privacy loss or not? There will be. In reality, we know that there will be, right? But if we want to go with the differential privacy setting, I mean, if you change the data of the woman, right, nothing will change in the outcome of the algorithm, right? So if you want to look at from the perspective of the woman, basically we didn't affect the outcome, right? So the issue here is that there is a correlation between the data of different users, which will be ignored. So if a user is not, for example, participating, but their data is correlated, then some information about them will be revealed, which we do not consider when we're talking about the differential privacy. This was also the exact issue that happened within the Cambridge Analytica. So in the Cambridge Analytica, I think like the number of people that shared data was around 18,000 people or so. And the, like the leaked information was much more than that. I think it was more than like a couple of million people's information was revealed. And the reason is this correlation. If I know about you, I also, even if your friends are not sharing anything, I will know about them, right? So the differential privacy is blind to such data externality. And as a result, we need to define a different privacy definition, which will also include this correlation information. So we call this the revealed information or information leakage, or the basically how much you are going to learn more about each user given the current signals. And we are defining it as follows. So basically, you would like to know for every parameter of each user, how much is revealed to, how much you know more about that theta, considering the revealed signals so far, okay? So if I want to think about this, so how can we say how much is revealed about a person? So of course, we are still uncertain about their values, right? But this uncertainty can become lower. How do we define uncertainty? Just the variance, right? So basically, I have some uncertain information about your type. At the beginning, the variance could be super large. But then, over time, this variance, if I have more information, this variance becomes lower and lower, which means that I know more, which means that it revealed more information. So basically, the reduction that we will have after observing the signals, the data, in the information, in the variance of the information about a person, that would be the revealed information about that person. So the reduction in the variance is basically how we are measuring the revealed information. And sometimes they call it information game, sometimes they call it value of information. And if you are going back to the example of the brother and the sister, even if it is just a function of the type of the brother, now since there's a correlation, I know that the variance of the DNA that I have for the sister will be lower, which means that there is a leaked information about the sister. And as a result, I can capture that with this notion. This is also the notion that mostly will be used for example, personalized pricing or, for example, advertisement. Note that there you would like to know the individual preferences separately. You don't have a common goal. It's not like, for example, a drug efficacy for all the users. It's basically you would like to know whether this specific person is interested in chocolate or not, or whether this specific person is interested in this political ad or not. Okay? So you would like to know personally more about this person, and as a result, you would like to decrease the variance that you have about the type of this person. We are going to talk about this also briefly at the end. And so what we can do next is that we are going to jump to the problem that we wanted to study. So we are going to talk about how we can monetize data. And we are going to look at two questions. So first of all, we would like to understand how we can optimally incentivize people to share their data while allowing them to have various preferences for their privacy. We are going to consider the differential privacy notion here, and we would like to know what would be the right mechanism there. And the second part of the talk, I'm going to look at the correlations and talk about if I compensate people just for their data, how disastrous can it be, like whether there are any remedies. And then at the end, I'm talking about some other also issues that needs to be addressed in future. So these are based on joint works with my amazing co-authors, Daron, Ali Reza, and Asu. Okay, so here is the main problem that we would like to study. So the first part, I'm going to look at the data acquisition problem. So data acquisition problem is basically how companies for their service can get the data. So right now, how do they get it? They provide service. You use their service. They gather your data, right? So for example, if you are using Netflix, if you are watching movies, they understand what you like. And based on those preferences, they're trying to tune your personalized preferences personalized suggestions, and basically each time that you go there, they say, based on blah, blah that you watched, we think you would like this, right? So they will, based on those information, they also improve their service. The monetization in Netflix is, of course, subscription-based. So it's not advertisement, but subscription-based. However, the improvement in the service and their popularity is because of the great service that they have, which is because of gathering your data. There are also other free services that we are using. For example, we are using Facebook or from the Meta, and what they offer you is a free service. You are using their platform for free. You pay no subscription. What do they gain from your usage? Your data will be used, and then you see a lot of irrelevant advertisements or relevant advertisements, which generates a lot of money for the company, much more than actually the service that they provide to you in exchange for user data. So these are two ways of getting the data for the companies. But then recently, there are some companies that, in fact, offering direct payment. So for example, Nielsen is an example that is basically offering a flat payment for if you are agreeing to share your data, for example, for a period of time. And it is not a single example. So there are other companies that are trying to actually give you more flexibility in terms of how much you want to share or in what level of granularity you want to share in exchange for payment. Okay? So this would suggest the following. So we are saying, OK, this is a data that I own. I am the owner of my data, right? So why not treating it as a commodity? This is my data, and I care about my privacy. So I have a cost for my privacy, and at the same time, it's my data, so I should be able to put a price on it and share it with the platform. So if the platform compensates me, then it would be fine, right? So basically, we would like to see if we give users agency for their data, if we let the users own their data, let them set their privacy preferences. So they can say exactly, instead of like Nielsen that is just offering a flat price, letting the users to actually say exactly how much it would cost them for different privacy losses. And then based on that, trying to figure out what would be the personalized compensation via either service or payment. Okay? So basically, we would like, instead of offering everyone a flat service that is the same for everyone, letting different people to be compensated in different ways and be able to actually tune their own privacies. Okay? So that would be the main motivation that we have for this part. And again, I will focus on differential privacy. So the two questions that we should address here are the following two questions. So the first question is, first of all, if I know the diverse privacy requirements for different users, and if I have a machine learning task, if an estimation task, what would be the best way of doing this estimation? So let me give you an example. Suppose that you want to do a mean estimation. Okay? So normally, basically, if it is like independent draws, you will get the average, right? But then if I tell you that no, in fact, this person who is sharing the data, who is like his data is available on the platform, is very privacy sensitive and wants to have a very strict like epsilon of very small amount, okay? Then this data cannot be like averaged out with a weight of 1/n, right? I would like to give a lower weight, for example, to this person, or potentially make it more noisy, right? So the question is that if I want to do the estimation task, mean estimation task, okay? And if different users have different privacy considerations, what would be the best way of doing it? How can I find the best estimator while I respect the privacy considerations, okay? So that would be the first question. The second question would be now, suppose that instead of just specifying this epsilon i's, these privacy loss levels, suppose that they are giving me a cost function. So basically, they will tell me how much would be the privacy loss cost for them. So how much would it cost them, okay? And then as an optimizer, I will optimize how much privacy I will give them and how much I will compensate for that, okay? So that would be the second question. Of course, they can always lie and tell me that my cost is really high to either get a very good privacy or also get a very, very good compensation, right? So we would like to also incentivize that, and that's the part that the mechanism comes back to the picture. Okay, so what I will do in this talk is I'm going to consider a platform who is trying to estimate an underlying parameter. For example, we would like to do the mean estimation task based on the data collected from the users. We assume that users' data come from a common underlying distribution. So while I know that these users have a common underlying distribution, for example, like how much they are interested in a new feature that a company have, I don't know that distribution. Okay, so this is something that I do not know, but I want to, for example, learn the mean of that distribution. Okay, and you would like to estimate the mean of the underlying distribution. So you don't know that, but you would like to estimate that. And of course, users benefit potentially from this outcome. So if you have a better mean estimation, you will better be able to tune the features of your platform. So we will assume that there will be a positive benefit from a better estimation. But at the same time, they have privacy consideration, and they want to consider the privacy consideration as well. And we formulate this problem as a mechanism designer problem. So basically, a user shares her data in exchange for monetary reward or service. And each user has different privacy sensitivities, which basically will be represented by the cost per unit of privacy loss. So it would be, we assume here, a linear cost function, but can be generalized to other sort of cost functions. And then individuals participate in the mechanism by basically reporting this cost parameter to the platform, and then the platform will decide how much privacy will give to each user, how they will use this the information in their mean estimation question, and then how much monetary payment they should give to the user so that they will respect the user's privacy. So the first thing we will do is that first we will look at the heterogeneous privacy levels. I insist on the heterogeneous privacy levels because for the homogeneous case, it's much simpler, and it has been studied. So the novelty of this one is that we can allow different users to have different privacy losses. And for different for different privacy loss levels, we show that what would be near optimal mean estimator that would respect to the user's privacy levels, both in the two architectures in differential privacy that I will talk about. And then we are going to allow users to declare their costs, basically their privacy sensitivities, and then we will solve the overall problem of like how much privacy I want to give to each person, as well as how much I want to compensate them, and then what would be the best way of like aggregating the data. Okay? So we show that there exists a polynomial time algorithm to find this optimal mechanism. And as I said, this mechanism simultaneously determines what would be the optimal estimator, what would be the compensation for the privacy for the users, and what would be the privacy loss on individual in this mechanism.
Do we have an assumption how correlated users are in terms of their data?
So we do not assume correlation among the data of the users, but there will be a common parameter, of course, the mean of the distribution, right? Which is the parameter that we are going to use. And note that this is not, as I will define in the platform's learning problem, the parameter that will be estimated is just the mean. And we are not trying to understand exactly what would be the theta I of the users.
But if we assume there is no correlation, but in reality there is, then we will not be able to guarantee the privacy they are asking.
Yes, exactly as you say. So for now, we are going to assume that these are independent draws from a distribution.
Thanks.
Okay. So from here on, what we are going to talk about is, first we are going to define what would be exactly this platform's learning problem. What does the platform want to do? Some basic definitions. Then I'm going to talk about the minimax optimality. So basically, we are going to talk about if you know the privacy consideration, if the privacy losses are specified, what would be the best way of doing the estimation? And we are going to define that in the best way as a minimax optimal. And as a spoiler alert, we show that the linear estimator would be sufficiently good for us. Then we are going to talk about the mechanism design problem. So then we are saying that, OK, we know only the costs, the privacy sensitivity costs. Based on that, define how much you want to give losses to the people, how much you would like to compensate them, and then what would be the best estimator that you will have. Okay? And then at the end, I'm going to talk about other works related to the data market. So let's start from the platform learning problem. So basically, you have a platform who wants to learn the population mean mu. So this mu is the thing that we would like to know, and we don't know. So we know that everybody is coming from an underlying distribution. They are from the same, for example, category. They are living in the same neighborhood. That's what we know about them. But we don't know the mean of that distribution. And examples for that could be, for example, there's a pharmaceutical who wants to learn how efficacious the new drug is, or you have a new feature for a platform and you would like to know how much users like that. So these are the things that we would like to know. So basically, there is some global estimation objective function that you would like to learn, some global parameter that you would like to learn, which would also be useful for the users, and that would be also the goal of the platform. And there are n users, so each of the user has a data, theta 1 through theta n. These data points are coming from an underlying distribution, but that has a mean mu, but we don't know this distribution p. So we know that this P is belonging to a larger family of distributions. We don't know exactly which one. Now, what we will do is that, OK, here, the clicker sometimes clicks and sometimes not. OK, now the users are going to give the data either directly or after passing it through a channel to a platform. And then based on this data that is shared with the platform is going to generate an outcome, which we call it the mu hat, which would be an estimation for this mu. And the goal of the platform is to find the best estimator for this mu, basically best estimator mu hat for this mu, subject to the constraint that we have, unlike the most of the classical settings, when the users are sharing with you the data, you are not allowed to freely use that data. You have to keep in mind that the people are privacy constrained and they have some privacy losses specified that they would like you to satisfy. So basically, what would be the best way of learning while you are respecting the privacy constraints? So before I go more into the details, let me also talk about two main architectures that we are going to consider for the differential privacy. So recall when we were defining the differential privacy, we were saying that, OK, differential privacy is basically an outcome of the algorithm does not change much if just one user changes her data, right? That was the definition. Now, there are different ways that the users do not trust the platform. So either they are trusting the platform, they're OK if Apple is gathering their data, but then the outcome that the Apple generates, they want that to be private. So what will be revealed to the world, they want it to be private. Okay? So that's called the central architecture. So this is also the setting that is used by the census. And basically, users are trusting the platform and only requiring a privacy guarantee for the outcome that will be generated at the end. The estimation that you will have at the end by the platform, they want that one to be private, that outcome to be private. So that algorithm that we were talking about, we would like the outcome of that algorithm to be just private. Okay? Or it could be the case that you, in fact, do not trust the platform, which is most of the case for the users, right? They even do not trust the platform, right? So this is what, in fact, Apple is using the second architecture, which is called the local architecture. So basically, users, while they're using the iPhone, they are, of course, they cannot manipulate their data. Their data is how they are using the phone, right? But then they would like Apple not to store it as is. They want whatever data is stored for Apple to be privatized, okay? So this is the local architecture. So in the local architecture, the data that will be passed to the platform is supposed to go through a privacy channel. So there will be a privacy channel that the data will go through it, and then the noisier version of the data will be passed through to the platform, okay? So this is called the local architecture. This is the one that is used by also as an advertisement for the Apple to say that we are respecting your privacy. Now, if I want to formalize it, we are defining the central differential privacy as follows. So we are saying an algorithm is epsilon I central differentially private. So compared to the previous definition that I talked about, here I want to allow different users to have different levels of privacy loss. So I will define it as epsilon I. So I will say that this is epsilon I centrally differential private if, for example, if I change the data of just user I and keep everyone else the same, the distribution, the outcome distribution does not change much. And the change to be bounded by e to the power of epsilon I, okay? So the only difference here is that now I can give different epsilon i's to different users, even for the central architecture, right? And then this will guarantee different privacies for different users, okay? So this is the central architecture. And similar to the previous example that we talked about, if epsilon I is smaller, basically you have a better guarantee for the privacy. So as a result, I'm referring to it if privacy loss is larger, epsilon I is larger, I call the epsilon I the privacy loss. The other, yes?
About one-time data sharing platform, or no, it's like a streaming data that we are sharing?
No, it's one time. So everyone, like, basically they share their data and everything is there, and at the end of the day, you're going to do a learning task on those data that is gathered. Okay. So now for the local differential privacy, we said that you do not want to pass your data directly to the platform. It will go through a channel. So basically what you would like to have is that the distribution of the data that will be the outcome of the channel, you want to be differentially private. So if you change your data from theta I to theta prime I, the distribution should not change much from the outsider perspective. So it would be, the change should be bounded by e to the power of epsilon I, okay? And this would be the local architecture. So basically, one thing that you can observe here is that if you have a platform that is epsilon I locally differentially private, what you know is that you already privatized the data when you wanted to pass it to the platform. As a result, the platform doesn't have access to the original data, and as a result, like the outcome the algorithm can generate will be already centrally differential private. So if, for example, if you have an epsilon I locally differential private architecture, it will be also epsilon I central differential private as well. Okay? So it will pass through.
How these targeted?
Sorry.
How do you ensure that when the feedback, when the user, that what the user gets back is like dedicated to this, since basically this thing is private. Like how does you because
how do you privatize this? You're talking about no?
The target, the benefit for the platform, since they want to be able to target the user to provide targeted advertisement.
So we are not actually talking about the targeted advertisement here. So our goal is like we are more of a a good person here. We want to, for example, the objective of this platform is like it's a pharmaceutical who wants to design a very good, for example, drug for people. So we have like some objective, like a mean estimation of a population in mind, not like a price discrimination or the personalized pricing targeting here. So if you are privatize it, you can personalize it, but to some extent, right? Because we already have it differentially private, and that's the guarantee that you want to have. So basically, keep in mind the following. The data owner is the user, really, right? As a result, if they require you to have epsilon I differential privacy, that's how much you can extend the personalization, right? Okay, so now let me actually tell you what is the common approach that is used for differential privacy. So while everything looks very magical and like so sort of like terminology is sort of complicated, the way the differential they make something differentially private is very simple, and it's called the Laplace scheme, which is basically by adding a Laplace noise. Okay, so let's actually recall what was the Laplace distribution. Let me just bring that up. Okay, so basically, why is it going? So let me just stay here. So it will. Okay, so we have the Laplace distribution, and recall what was the Laplace distribution. It's like a normal distribution, which is pointier a bit, and also with fatter tail. So adds more noise compared to the normal distribution, and also it's like more pointy, right? So we are assuming that this Laplace noise that we are adding has a mean 0, and it will have some scale, which we denoted by 1 over eta. And basically, the distribution, the PDF distribution of the Laplace noise is the following. So it would be, if you are at the scale of 1 over eta, the probability of any value z happening is eta over 2, e to the power of minus eta, absolute value of z. Okay? So keep this PDF distribution in mind. Now let's actually see how this Laplace noise is coming to help us. Okay? So for example, consider a linear estimator. What do I mean by a linear estimator? Basically, I have n data points. I will get the weighted average of these data points. So basically, I will calculate the summation of wi theta I subject to the wi is equal to 1. And then at the end, I will add a Laplace noise at the end. Okay? So I would like to see whether I can get anything in terms of the differential privacy guarantee if I add this Laplace noise. And most of the like the classical differential privacy are just by adding this Laplace noise. Okay? So let's see. What was the definition that we have? So basically, if I want to see how differentially private this mechanism is, what I want to see is that I would like to see that if I change a data of one user I from theta I to theta prime for any theta, what would be the change in this probability distribution, right? Let's actually see what would be the probability that mu hat would be equal to t. So basically, it would be the probability that's the summation of wi theta I plus this random variable z will be equal to t, right? So in other words, if this wants to be equal to t, z should be equal to wi plus wj theta j's minus t, right? And then there will be like that would give me the difference that I want to have for the z that I will have here, right? So basically, you can write the equation here, and you can see that exactly the probability of this event will be bounded by eta wi times the difference of the theta I and theta I prime. And here we assumed a bounded support. So basically, this would be bounded by 1. So this will give you a guarantee that this ratio will be less than or equal to e to the power of eta wi. Okay? Now, for the differential privacy, we said that this should be less than or equal to e to the power of epsilon I. So this would suggest that if you have a linear estimator where the weight that you will give to the data of one user is wi, and you add a Laplace noise with a parameter of 1 over eta, then it would be eta wi differentially private. This is more this is a result by the work, and it's more general than that, as you can imagine. Basically, you can just say replace this wi with the sensitivity of that function, and it would be eta times the sensitivity of that function with respect to the data of the user I. Okay, and that would be how much it would be differentially private.
Is that the reason why you choose Laplacian noise? Does the deep long tails play a role?
Yeah, long tails add a lot of noise, right? So like it makes it like more noisy, which gives you a better guarantee like this, right? So the normal is too much concentrated around the mean. But there are there are other. So one thing that sometimes we will have problem when we are dealing with the Laplace noise is that if you, for example, have two parts of your mechanism that you want to make it differentially private, when you are adding noise to one part and adding noise to the other part, you need to be able to say something about the combined distribution. That's where you will go to the Gaussian, and then you will change a bit the definition of differential privacy, and you will go with the Renyi differential privacy. Okay. But the classical results are mostly based on the Laplace scheme. Okay. So I just wanted to for you to have some idea of like how differential privacy will happen. So basically, if you have a linear estimator, you will just add a Laplace noise, and then it will make it differentially private. So now the question that you would like to understand is that how much should be this parameter eta, and how much you want to set, how you would like to set these wi's. So the problem will be simplified to the following setting. So from here on, what I'm going to do is that first I will assume these epsilon i's are given to me. So I would not consider like optimizing over epsilon i's. I will assume that these privacy losses are fixed by the people. And then we show that the linear estimator with the Laplace noise is near optimal with respect to the mean squared error. We are doing the mean estimation. And then we are going to endogenize the choice of the privacy loss. So basically what we are going to do is that we are going to ask, tell me what are your privacy sensitivities, the cost that you will have for privacy. And then I will try to figure out what would be the best way of designing these wi's, the privacy loss guarantee that I want to give to each person, and also the compensation. This will be, of course, a mechanism design problem, which we will see how to do it. And then we characterize also how exactly we can calculate this optimal mechanism using the Laplace scheme. Okay, so next we are going to talk about the minimax optimality. So first, let me define what is this definition of the minimax optimality. And the reason we do this minimax optimality is that I would like, at the end of the day, to tell you that when I'm using linear estimator, I'm not doing a bad thing. Okay? So basically, linear estimator is a very good simplification when you want to do the estimation, right? Because it's very simple, it's linear, right? And as a result, perhaps you would say that, okay, it would be easier to calculate the wi's. Why did you go with the linear estimator? So we will do the minimax optimality argument in order to defend the linear estimator and to tell you that, in fact, it is not that bad. It is close to the optimal to just go with the simple estimation method. Okay? So let me define the minimax optimality. For the mean estimation task, what would be the minimum estimation error for any epsilon I given that you can expect? This would be a lower bound that I want to guarantee. So basically, I do not want to specify what mechanism I will pick, but I will just tell you that I want to have epsilon I guarantees. And then I will ask you what would be the lowest error that you would incur, right? So it could be achievable or not. I just want to find a lower bound for that, okay? when I will then show that the linear estimator, while not completely matching it, it is close to that. So then it would be a good news. Okay? So that's how we are going to continue. And that would be the estimator that achieves this bound close to the optimal. So let me define the minimax lower bound. So suppose that the privacy losses of individuals are given, which are the epsilon i's, and we are in the central setting. So users are going to share data theta 1 through theta n with the platform. The platform is going to calculate mu hat. Okay? And then what we know is that this mu hat is the mean of a distribution P. Okay, so this is the mean of the, we would like to have this, the best estimator for the mean of this distribution, but we don't know what is this distribution. The only thing we know is that we know that it belongs to a larger class of distributions, which we do not know exactly which one. Okay, so the worst case estimation error of mu hat over a family of distribution math calp will be defined as follows. First, for every mu hat that you give me, I can see how much the difference would be for every potential P, right? And then I will get the worst case. So I would like to see for which of this, if you fix this mu hat function, for which of these distributions in this family, it will give you the worst bound here. It would give you the worst estimation error here, okay? So first I will calculate this. And then I will say that, OK, now knowing that, find the estimator that over all these worst case guarantees, find the best, minimizes that. OK? So that would be my lower bound for the worst case estimation error. OK? So is the definition of the minimax lower bound clear? Okay, so now we would like to do the figure out how to bound this. And this is a classical minimax lower bound. What we want to also specify here is that this mu hat that you are going to generate here is supposed to be epsilon I differentially private. So in other words, this mu hat is supposed to belong to a subset of potential estimators that you have. Not all estimators are acceptable here. Okay? And among those, we would like to know what would be this minimax lower bound. So the results that are known for this setting is when we have homogeneous epsilon i's, meaning that if all epsilon i's are equal, basically it's a seminal result by Ducci et al. That they showed that linear estimator is in fact real minimax optimal. But in the heterogeneous case, there is no result. And what we will show is that the linear estimator is near optimal here. Okay, so let me first define what is a linear estimator here for the which is differentially private. So basically, we are defining a linear estimator that is differentially private as follows. Suppose that the data are theta 1 through theta n. First, I will decide about the weights w1 through wn. I will get the weighted sum of the data points, ensuring that the sum of w's, of course, is 1 because I want to get a weighted sum. And then I want to make it private. So I will add a Laplace noise at the end, Laplace of 1 over eta at the end. And that would give me like the my estimator. Okay. So this is the definition of the linear estimator. And you recall from the definition that we have for the Laplace distribution that this mechanism is Wi eta differentially private, right? So basically what we would like to have is that we are supposed to, if we are focusing on linear estimator, we would like to find Wi and eta such that for every individual I, Wi eta is less than or equal to epsilon I. So you will give a better privacy loss than the epsilon I required.
How many times we can do that? How many queries we can have? Are we going to get mu hat only one time? We can ask one, or no, we can do it several times.
No,
and
no,
every
it's just
time
once.
only one time.
Yeah.
Okay.
So now This estimator, as we said, is eta wi central differential private. And what we would like to have is that we would like this epsilon wi to be less than or equal to epsilon I that is required by the mechanism. Okay. So I would start with the positive result. So I would say I would like to see what would be the best, like how we can optimize over the weights that I want to choose for the linear estimator and how I would decide about the eta. And then we will go over the lower bound result, okay? So basically here is the overall result that I will show you. So what I will show is that given the epsilon I privacy loss requirements, there exists this bound which depends on the summation of the epsilon i's squared, and you are going to maximize over all potential values from 0 to n. And this would be a lower bound on any minimax estimation error that you will have for any mechanism that is epsilon I differentially private. And we show that a linear estimator with the Laplace mechanism, you can choose wi's in a smart way so that you will more or less match this bound, okay? So what we are going to do is that we are going to start with the second part. So first we would like to see the constructive part where we would like to know if I give you the epsilon i's, and if you are focusing on linear estimators, how do you decide about the wi's and eta? What would be the best way of choosing this in order to minimize your estimation error and respect the privacy? Okay, so we have user 1 through user n. Their data are theta 1 through theta n. And suppose that you would like to do, and the data are independent draws from the distribution, and you would like to find the best estimator. If I have no privacy restriction, no consideration of the privacy, how do you design the estimator here? What would be the best way of defining the mean estimator here to minimize the mean squared error? Average, right? Simple average, right? So basically what we will do is the following. Let me just stand here so it will not go that much. Yeah, so you will set all the weights equal, right? You will get all of them the weight of 1 over n, and that would be nice, right? Now, the other case is suppose that you want to have similar privacy demand for all the users, right? So again, here, as we will expect, we will give all of them the same weight, right? Because that's the mean estimator. If you don't have any privacy consideration, you also give the same weight. So as a result, for the second case, also we are going to give the same weight. Okay? That's good. Now, suppose that the epsilon i's are, I sorted them in an increasing order. So the epsilon 1 is smaller than epsilon 2 up to epsilon n. How do you think we will change the weights? So if epsilon is small, what does it mean? It means that I want your data to be super noisy. I don't want to see much of your data, right? And if the epsilon I is large, it means that it's okay. I can even just directly use your data, right? So with that in mind, how do you think the weights will change? Okay, so let's see. So basically, we would like to have the lowest impact here and the highest impact here. And basically, so it could be the case that we are going from W1 through Wn sorted in this order, right? But again, we should keep in mind that there are two forces here. One of them is like, okay, we care about the privacy losses, and we know that if data is very noisy, it's not a very informative information, right? But at the same time, when your data is not noisy, so for example, for the last part, if they are not that noisy, what you would like to have is that you are not going to, you care about to give also sort of similar weights to them, right? Because you would like to also act on the stochasticity of the data, right? So for example, in the first case, we know that we want to give all the weights equal to each other, right? Because we want to cancel out the noises, right? You do not want to bias too much for one data point compared to the other one, right? So as a result, when you solve the optimization problem, so basically, if you go with the weights sorted like this and set it exactly equal to, so set the WIs exactly equal to, for example, epsilon I, WI eta equal to epsilon I, or in other words, epsilon over eta, then probably you will give too much weight for this tiny fraction, and as a result, this will not be a good estimator, right? So if you look at this optimization, you have this constraint. So basically, if you want to look at what would be the convex optimization that you're supposed to solve, basically, you are trying to minimize the estimation, a squared of the estimation error that you will have for your mean, which is basically the variance times the summation of the weights squared plus 2 over eta 2. Subject to that, the WI eta should be less than or equal to epsilon I, which is the guarantee given to you, and also the summation of the WIs should add up to 1. Okay? So this is the program that we want to solve, right? And then if you write just the optimality condition, the necessary optimality condition, the KKT conditions, what you would see is the following. So basically, in the optimal estimator, for the users that have like a low, they want to have high privacy guarantees or low privacy losses, the W's will be sorted and exactly will be proportional to their epsilon I. So in other words, these constraints will be tight, okay, in the optimization. But there will be a threshold after which the weights that we will give to all users will be the same, okay? And this is the part that you will no longer will have tight bounds here, okay? So basically, you will set it lower than the epsilon I's, okay? If you write the KKT condition, this will also automatically comes out of the KKT condition. And since we want to match it to the bound that we have for the lower bound, we need to actually decide, like algorithmically also, to suggest a way of choosing the weights. So one way of choosing the weights is to find the first epsilon I that is above 1 over square root of n plus 1 minus t. And from here on, basically set the weights for the first n minus k minus 1 user, set it tight. And from here on, set them all equal to each other. We will get exactly the bound that we have in the slide. So basically, here is the takeaway. So the optimal linear estimator, if all the epsilon i's are the same, would be equal weights. But if you have heterogeneous privacies, there will be a threshold-based structures. For users who demand a privacy loss below a threshold, the weight will be proportional to the epsilon that they actually requested. While for all users that demanded a privacy loss above a threshold, they will have the same weight, meaning that they will get a better privacy guarantee compared to what they asked for. And this is because of the data stochasticity. So now, the next thing that we are going to do, we are going to talk about the minimax optimality, which would be, I will briefly talk about it to give you some idea of how these minimax bounds are proven. So usually in practice, you care more about the positive result, which is basically the constructive solution for finding WIs. But from the theoretical perspective, or if you want to defend your method, the minimax approach is very useful. Okay? So in order to show a lower bound, there is a method called the LOCAM method, which is basically connecting this estimation task to the hypothesis testing. So let me tell you how we can reduce the lower bound to a hypothesis testing. So suppose that you have n data points, theta 1 through theta n, where they're coming either from distribution P1 or distribution P2. Okay, they are drawn from P1 or P2. Okay, so we said that there will be a family of distribution where your data comes from one of them. Suppose that those distributions are P1 or P2. Okay, So I have, they're coming from either of these two. And then the estimator is going to decide about what would be the mu hat for the best estimator that it can have for this data. And suppose that the distribution of the estimator, if the real data comes from P1, is mu hat is distributed by Q1. And if the real data is coming from P2, the distribution of mu hat would be Q2. Okay? So is that clear so far? So I have two distributions, P1 and P2, right? And I know that my data belongs to either P1 or P2. I don't know which one. Okay? Now I'm designing an estimator mu hat. What I can say is that if the data was coming from P1, the mu hat distribution would be like Q1. Okay? If the data is coming from P2, the mu hat outcome distribution would be Q2. Okay? Because mu hat is a function. For example, it could be like the average, right? Then you can say that, okay, mu hat distribution would be like this or like that, because you have n samples. There's randomization also associated with that, right? Okay, so you have Q1 and Q2 as the distribution of the mu hat. Okay. Now let's actually look at it as the hypothesis testing. So I have a mu hat that is either coming from the Q1 or Q2. I'm giving you the mu hat, and you would like to figure out whether it's 1 or 2. Okay? So the hypothesis testing is supposed to tell me whether it's 1 or 2. Okay? That's the test. Okay? So there is this known result that the probability of error of any test is at least 1 minus the total variation distance of Q1 and Q2. So the total variation distance of these two distributions will be 1 minus the total variation distance will be the error of any test that you have. Okay? Okay, now let's actually see how we can get back to our lower bound. Okay? So consider the following test. Suppose that when I see mu hat, so I know what is the mean of P1 and I know what's the mean of P2, right? So when I see mu hat, I would see which one is closer to mu hat. Okay? And the result of the test would be, I would say that J is that one. Okay? So for example, if mu hat is closer to the mu1, I would say the outcome is 1. If it is closer to mu2, I would say the outcome is 2. Okay? That is how I'm responding to the test. What we know is that for any test, this error, the error that it makes is greater than 1 minus this distance, right? And suppose that we call the distance between the P1 and P2, the half of that distance, the radius of the distance, by gamma. Okay? So each time that I make a mistake here, what does it mean in my test? So basically, I have a test. Sometimes it's returning a wrong answer. Okay? What does it mean that it is a wrong answer? The one that was closest to me was the wrong answer. So in other words, the right distribution to me was the one that was further away from me, right? Or in other words, my distance from that one was at least gamma over 2. Gamma, right? Was at least gamma. Each time that I'm making an error, mu hat has a distance of at least gamma. Right? And then we know that actually the probability of the errors happening is at least this much, right? Now, putting these all together and looking at the mean squared error, basically it would be gamma over gamma squared times 1 minus, so this probability times the gamma over 2 will be like basically the amount of error that you are making in your estimation, because each time that I'm making an error in the test, my distance of mu hat from the original one is at least gamma, which is what we were looking for. I wanted to bound the distance of the mu hat, the estimator, from the real mu of the distribution, right? I was caring about this distance, right? So as a result, this is the Locan method, which basically says that the worst case mean squared error is bounded by 1 over 2 gamma squared times 1 minus the total variation distance of Q1 and Q2. Okay? Now, what is the next task? So basically, knowing this result, it's a very like standard approach. After the Duch's result, you will decide about P1, and so you want to make this lower bound the worst possible. So you are going to choose P1 and P2 in a way that you would like to make gamma large while the total variation distance is small, right? So you are going to carefully choose that, and as a result, you will get the lower bound. Now, when we want to plug in the differential privacy information, I will not go over the details, but basically, in order to be able to apply that, you need to somehow be able to use the chain rule, because differential privacy is defined by changing the data point of one user at a time. And as a result, basically, you're going to use also the Pinsker inequality here so that you will have access to the KL divergence. Okay, so I do not go over the details of how we get this bound, but actually it has a very nice proof, but the basic idea is the Pinsker inequality, just that. So now the same results, we can get similar result for the local setting. So basically, if you have given epsilon i's, again, you can show that the linear estimator will be approximately optimal in the local setting as well. Okay. And the idea will be similar, just the only difference is that the weights that we will give in the linear estimator will be all proportional to the epsilon i's. So here we no longer will have all the weights being equal at the end. And the lower bound is, again, based on the locam method. So anytime that you want to do a minimax bound, think about the locam method. It's becoming very handy. Okay, so now I want to get to the mechanism design part. I would like to know how I can design the mechanism. So far, we were talking about that, okay, if you are giving me the epsilon i's, how can I design the best mean estimator? We said that, okay, there is a bound that you cannot do better than that using Lecam's method. And then I can actually tell you that if you use a linear estimator, which is basically getting the summation of wi theta I plus a Laplace noise, this would be not that bad. So we were saying that it's OK to go with the linear estimators. Next, what I want to tell you is the following. Suppose that instead of epsilon I being given to you, suppose that you have privacy sensitivities. So basically, a user will tell you that if you give them a privacy loss of epsilon I, how much it would cost them. And they will define that cost with the cost value Ci. Which is coming from a distribution. This is a private information, of course, to the user. Each user knows their own privacy sensitivity. So I might be sensitive for the other people to know whether I like chocolate or not, while some other people may not be sensitive. Okay. Now, users are going to report their privacy sensitivities CIs, and it's not necessarily truthful. And these sensitivities are different from their data. So for example, on the Apple, when they are gathering your data, you can tell them, actually, I do not want you to use my data much. I'm very privacy sensitive, but I cannot manipulate my data. So these two are completely different from each other. While Apple can see which routes I'm using, Apple may use it like as is, or may add noise based on my privacy sensitivity cost function. And depending on the reported privacy sensitivities, the platform wants to design what would be the compensation that they want to give to the users, as well as how much they want to give guarantees of privacy losses to the users. So basically, our mechanism at the end of the day, based on the reported costs, will decide about the privacy losses epsilon i's, and also it will decide about what would be the mu hat estimator that they will have, and also the compensations TI functions. Okay? So let me actually put them in one picture so that we will understand it better. So again, we are going back to the setting that we have n users. They have a data of theta I. And also, they have a cost, the privacy sensitivity cost function, CI. So this is like a scalar, a number, which is saying that how sensitive they are in terms of like the privacy loss. We know the distribution of this cost function, but we don't know exactly what is the cost for each user. Okay, so it's a private information of the user. And then they are going to report to the platform their costs, this privacy sensitivity cost, not necessarily truthfully, of course, right? They will decide, like they are rational agents, they optimize that. And the mechanism will return the following. It will return a linear estimator mu hat, the privacy loss levels epsilon i's based on the reported costs, based on the reported privacy sensitivity CIs, and the compensation for the users, the TIs. And the goal of the platform is the following. While they want to minimize the estimation error that they will have, they have to pay the users, which is not for free. So as a result, what they want to minimize is that they want to minimize the mean estimation error plus the payments. And here I just naively summed up. You can add some, like, for example, a multiplier for each of the terms. So that you can add like a constant here or here based on the setting that you are working with. Okay, so this is your goal. And we study mechanisms with estimators that provide both central and local differential privacy. For the talk, I will just focus on the central setting and will not go back to the local at this point. Okay? I went back. Okay. Okay, so now one thing I want to add here is that, do you remember at the first part of the talk, we talked about how we can design these mechanisms, right? So we said that you already see the FI here, right? So you can guess that I'm going to talk about Bayesian mechanism design, right? I want to design a Bayesian mechanism where I do not know the type of the people, but I know their I know the distribution of their types. And then we said that when we want to do a Bayesian mechanism design, one thing that is really useful is the concept of the revelation principle. What was revelation principle telling us? It was telling us that it's without loss of generality to focus on the class of mechanism where the best strategy for each user is to tell the truth. Okay? So as a result, I should get here. Okay, so we are going to focus on truthful mechanism, and the platform is going to decide about the compensations and epsilon i's, such that it will incentivize users to report their cost functions truthfully. And this is without loss of generality because of the revelation principle. Okay, so now it's time to define what would be the cost function for the user. Okay, so let's see what is the user cost function. So user has different terms. So it will get a compensation, right? We know that. User care about a good drug, so they will benefit from a better mean estimation error. They also care about their privacy, so it will cost them to have a privacy loss. So basically, I will treat mean estimation error also as a cost that I want to minimize, right? So I will say that there will be 3 terms in the utility of a user, which I call it the cost of a user. So the first term is the cost of the mean estimation error. So if your mean estimation error is worse, it will cost you more, right? So that would be the first term. There will be the second term, which is the privacy term. So we are assuming that it is linear in the cost. So it would be the CI multiplied by the privacy loss guarantee that will be given to the user. And note that this epsilon I will be a function of the C prime I. But when you want to calculate the cost of the user, you should put the real type of the user here. So it will cost per unit of privacy loss CI times how much privacy loss they will be given. And then the last term is a benefit. So as a result, it's a negative compensation. So if I get some money, it's a benefit to the user, which is basically a negative of the cost. So minus the compensation. And we also need to look at one more thing. It is, I am a user. I have the option of not participating in the mechanism, right? In the mechanism design, we call it also the IR, or individual rationality, which is basically you would like to give the participants voluntarily participation. So in other words, if this person stays out of the mechanism, you should see what would be the utility that the cost that they will have, and you want to ensure that their cost in the mechanism is not higher than the cost that they will stay outside. So you can see that if you calculate, if you stay outside, you will not get any compensation. You will not have any privacy loss because we are assuming no correlation here. And the expected mean estimation error that you will have, basically you have your own data, which is what you will use for your estimation, nothing else. And as a result, like the noise that it will have, or the mean squared error, will be just a variance. Yes?
But why users should care about MSE? I mean,
Because, for example, you can think it's the quality of the service that you will get. You can always ignore that. So this term is not necessarily for the result. We just included that because we thought that some people might think that it is relevant. But you always can put a very low weight, or in fact, remove it from the problem, and nothing will change. So if, for example, this was not there, it would be 0. Yeah.
I of ci prime and c minus I prime, or
So it is the epsilon I of c prime I and c minus I. The reason I'm putting just the c minus I here is that I'm going to say that in the equilibrium, everyone is going to play truthfully. So when you want to look at the cost of this person, you would assume everyone else is playing in the equilibrium, and you can consider what would be the cost that it will have for you for different actions. Okay, so now let's actually write the mechanism design problem. So your platform wants to minimize the objective, which is basically as we said, we have a mean estimation error, right? A mean squared error of the mean estimation. This is the first term. I want to minimize that. And also, I don't want to pay much, right? Plus the compensations. Again, you can add weights here to solve it. Subject to the incentive compatibility constraints. And exactly as we saw before, using the revelation principle, it's subject to incentive compatibility, which is basically the best strategy for every user is to tell the truth, and also the individual rationality. So individual rationality, as I said, is the voluntarily participation. So if you satisfy these two, you're done. So basically, you would like to find the compensation and epsilons and mu hat in a way that you would minimize this, and at the same time, this would be the best strategy for everyone is to tell the truth, and everybody voluntarily participates. So there are many constraints that we want to optimize, right? So let's see how to deal with it. So if I want to write it in the the incentive compatibility in terms of the formulas that we learned, so basically incentive compatibility states what? It says that the user cost, if you tell the truth, will be minimized, right? So in other words, incentive compatibility is saying that if you tell the truth, your cost will be lower compared to if you tell, if you lie. And as you pointed out, we can assume that the other individuals are paying in the equilibrium, and as a result, they're telling the truth. And the individual voluntarily participation, it just says that the cost of participating is lower than just staying outside, which was equal to the variance. Okay. So if I focus on the linear estimator, as was the promise of the Minimax bound, the platform's optimization will have the following parameters to decide about. First of all, for the mean estimator, we are going to decide about the weights that we are going to add to each of the theta i's. So it would be the summation of wi theta I plus a Laplace noise, right? So I should decide about this wi's. I should decide about this eta. And then these would give me some epsilon I, right? So if I decide about the epsilon I, the wi and the Laplace noise, this will give me some guarantee about the privacy loss, right? As we saw before. And you also need to decide about the room is too big and I move too much. So it's so okay, and the compensation. You should also decide about the compensations, right? So these are the things that you are making a decision about. And there are a lot, right? It is all the W's, eta, all the epsilon i's, and ti. And you have this mean squared error here, and also ti, which is like a monster here, and also like this cost function, which depends on all of them. Okay? So let's see how to approach them. So let's start with the incentive compatibility constraint. Okay, so basically what we would like to have is that we would like to have the definition of the cost function for the user. If they tell the truth, we would like it to be lower than if they lie and they declare their cost as C prime I. Now, the good news is that when I want to optimize over this cost function, if I want to minimize this cost and I would like the minimization to happen for the C prime I being equal to the Ci, the payment identity that we saw earlier in the first part of the talk, you remember when we were talking about the mechanism design and the revelation principle, we said that the good news is that if you look at the truthful mechanism, there is a payment characterization. So basically, you can write your payment in terms of the allocation. And it was simply by just taking the first order condition and like saying that it will be satisfied at the truth value. Okay? So here you can do exactly the same. And that will give you a characterization of the payment characterization for you in terms of the mean squared error and also the epsilon I, which are basically your allocations. So this will give you a way of at least getting rid of one of the parameters that you were making a decision about, right? So for now, we know how to write payments in terms of epsilon i's and also the mean squared error, right? So this is good news. One of the parameters are moved. And we also need to have the monotonicity condition, which basically says that in the privacy loss that you will give to each user will be monotone, it's weakly decreasing in the cost that you will have. Okay? So if you have a higher cost, the privacy guarantee that you should get should be better. Okay? Or in other words, a smaller epsilon I should be given to you. Okay? So these two conditions are necessary and sufficient. So as a result, when I want to solve it, I can actually make the problem to go to be smaller. I replaced the payment identity in the objective. I didn't do any magic. It is just direct application of the proposition that we saw. And now the mechanism design problem becomes the following. So you are trying to minimize this subject to the green constraint. Okay? So one thing that is nice here is that the objective looks nice, right? And this phi of Ci that you see here, it's called, usually in the mechanism design, it is called the virtual value. So basically, the virtual value, when you are selling an item, it would be Vi minus basically the 1 minus F over 1 minus the CDF divided by the PDF. And it's a very important thing in the mechanism design because everything will be defined based on this virtual value. So basically, virtual value will define how much revenue you will generate in expectation for the seller, okay, in the selling settings. And here, similarly, it will tell you like how much it will cost the seller in expectation, okay? So this is the virtual cost. And so we would like to solve this problem, but one issue that we will have is that this is an expectation over all c minus I for the epsilon I, and we want this expectation to be decreasing in z, and it is a monstrous objective function that we are dealing with here. So one thing that we can do here is the following. We can be hopeful, so we can relax the constraint here and assume that it doesn't exist. We can try to solve the objective function pointwise, meaning that for every vector of epsilon i's, I will just see what will be the optimal solution for the objective function. And then at the end of the day, I can verify whether it is satisfying the condition or not. Okay? That's how we are going to look at the problem. Okay? And then we were lucky. So it will, good news is that the green condition at the end of the day will be satisfied. So basically, what we will do is that we will just trying to minimize this function for a given vector of epsilon i's, okay? Which is written here. So basically, I'm trying to minimize the n plus 1 times 2 over eta 2 plus summation of variance times the wi2. This is coming from the min estimation error, plus the term that is coming from the virtual values, summation of phi I ci times the epsilon I. And the only conditions that we will have is that this should be a valid mean estimator, so the summation of the wi should add up to 1. And also I should respect the privacy. So if I put epsilon I here, given that I'm using a linear estimator, the epsilon I should be greater or equal to the eta wi, because this is how much the linear estimator is guaranteeing. Okay? Okay, so what we will show is that, as I told you, assuming that we have a regularity condition, meaning that the virtual costs are increasing in C, then the solution of this pointwise optimal will also satisfy the green condition. So let's see how to solve the P central here. So we would like to solve this problem pointwise optimally. So the last step of our mechanism is this thing. We would like to solve this. Okay. So how should we solve this? So basically, the first thing that we can observe is that the place that we can see epsilon I here in the objective is just this term. It's a linear term here, right? So as a result, if this condition is not tight, I can just increase epsilon I, improve the objective function, and as a result, everything will be improved, right? So based on the optimality, what we can say is that, first of all, this condition will be always, this constraint always will be tight, right? And what it suggests is that I can replace wi by the epsilon I over eta, if this is tight. So it's basically, what we know is that the epsilon I will be exactly equal to eta wi, right? Now, I will replace the wi by epsilon I over eta. And then we have also one more condition. We know that the summation of the wi should be equal to 1. So as a result, this means that the summation of epsilon I over eta should be equal to 1, which means that eta will be equal to what? It would be equal to the summation of epsilon i's, right? So also I have a way of, okay, okay, here, okay. I went, just a sec, so I go back to where I was. Okay, here. So I will set the eta equal to the summation of epsilon I so that I will satisfy this constraint. And now if I do that, I will get to the following program. So I no longer have the constraints. And the only thing I have is that the epsilon I should be greater or equal to 0. And I'm trying to minimize this objective function, which is, again, in terms of the epsilon j's. And while this is much nicer, there's only one thing to decide about. This is not convex. So what should we do next? So the next thing that we will do is that let's actually first set summation of epsilon j's equal to some s. So suppose that I give you s. Okay? If I give you s, what it means is that this part, this term, will be replaced by s squared, right? And I would like to find how I should set the epsilon i's. Okay? So now the problem becomes convex, right? And the central problem becomes the n plus 1 over s squared, which is for now we are assuming is a constant, times 2 plus summation of epsilon I squared times variance, plus the virtual values times epsilon I, which is a linear term. Subject to the summation of epsilon i's being equal to s. This is a linear program, so basically you can write the KKT condition again here. And basically what you can see is that the KKT will tell you the following. If your virtual cost is greater than lambda, then you will give the guarantee of epsilon I of 0. Basically, you are not using that data, okay? And if the virtual cost is less than lambda, basically you are going to set the epsilon I proportional to this value, okay? So again, now you can see why virtual costs are very important. Again, in our setting as well, the key for each user is their virtual cost. So it depends on their own cost and also the distribution, right? So now what should we do next? So this is basically the KKT is telling me how we can decide about the epsilon i's, but we don't know where we are supposed to go, right? So for example, if I assume that the lambda that I'm picking is between these two numbers, between these two virtual values, I know the ordering of the virtual values, right? So if I assume that the lambda that I have is going to happen to be in this interval, what I can do is that for every lambda here, I can actually figure out what would be the corresponding s, because for that s would be equal to the summation of epsilon j, and I know that the epsilon j's for all the values below here will be exactly equal to this amount, and above that will be 0. So exactly I can see what would be the given s for that, right? And as a result, I can write everything in terms of lambda. Then what I can do is that for every interval, what I can do, I can try to find the optimal lambda. So basically, this would be a degree 4 polynomial, which since it is a degree 4, we are lucky we can find the roots for that optimally. And we can find the roots and find the optimal lambda corresponding to each interval. But then what should we do next? We should try that for all of the intervals. We search over all of the intervals, and we will select the one that's maximizing it. So that's how we are going to solve the problem. So here are the insights. So in both central and local settings, the platform's optimal data acquisition is thresholdy. So collect the data of a user if and only if his privacy sensitivity is below a threshold, and those thresholds are depending on the virtual cost of the user. And how these two settings compare. From the perspective of the platform prefers central. It is natural to assume that, right? Because the platform, if you have the data, again, thinking about it as a data processing inequality, if you have the data, you always can make it private at the end of the day. So you prefer to have the data and then make a decision about how to privatize it. So the platform prefers central. But from the perspective of the user, users actually, it's not clear. While we will expect that the local will be better, sometimes they may, in fact, prefer central, and the reason is that they care also about the mean estimation error. So because of that, sometimes they actually, in fact, prefer to go with the central because it can do a better job in the mean estimation characterization. So so far, what I talked about is when we have optimal data acquisition, when we have private sensitivity costs, and we made some assumption. Now, some interesting future directions that can be considered are the following. So here we are assuming that, for example, when I was comparing to the two settings and I was talking about the results, I was assuming that the costs for the central and local are the same. Suppose that it is not the case. Okay, so if the costs are different and if you can have both the local and central privacy, what would be the optimal mechanism? The privacy sensitivities and data, we are assuming that they're independent of each other, while in reality, sometimes when you are saying I'm sensitive about my privacy, it also signals something about your data, right? So like if, for example, specifically for the health, if people care about like their insurance cost not to goes up, and that's why they don't want the people know whether they have an underlying condition. So if you signal that your privacy cost is high, they will also perhaps guess that you have an underlying condition, right? So if these two are related to each other, what would happen? And there are other learning problems. So there were follow-up works that are looking at, we looked at the simplest learning task, which was mean, right? It could be regression, it could be variance, any other thing, right? So there were some follow-ups and that were looked at. And I think the most interesting is that what if users can misreport their data? I have no idea how to approach that problem, but that's a very valid question. Not for the platforms, at least like, for example, if the platform is gathering your data, there's no way of like misreporting, but at least you may actually strategize in terms of like how you are going to show your preferences. In fact, there were some studies that were, for example, for Netflix, the people knowing that the Netflix is showing the movies to you based on your preferences, they were running like this trials that people were trying to strategize how they are reporting their preferences. And in fact, there were studies that showed that people are really strategizing. So they are actually changing their preferences after they are acknowledged that your information will be used to change the order of the movies showing to you. So the question is that if they can misreport, what can you do? And then more on the data. So this is going back to the personal and price discrimination question that you were asking. So most of the time in the platform examples that we talk about, it's not about like a drug efficacy or things like that. Things that we care about and what we are really worried about is like this price discrimination, targeted ads, political ads that we see that is not relevant to us. They should not know that it is relevant to us at least. And that's what bothers us. And this is motivated by the second topic that I talked about, second privacy notion that we talked about, which was the data externalities. So basically, the data of a user will reveal something about the others as well. That will be the problem that we will have. And basically, in some other work, we looked at the externalities, and we basically talked about how we can design to protect personal information. It was like a very immature design. It's not a complete result, which requires to have like a third party that you completely trust and you will share your data with. But with that given, you would be able to at least do some sort of like mediation to improve the loss. And I will not have time to go through the model here, which is based on the revealed information. But basically, let me just go, just talk about some equilibrium inefficiencies that may happen in this setting that the data of the users are correlated. So there are two sources of inefficiency when the data of users are correlated with each other. The issue is that we have heterogeneous privacy considerations, and as a result, there will be leakages of for example, a person who really care about their privacy just because they're connected to the other people who have low privacy. There will be inefficiencies due to that. And even on top of that, when a high-value user where normally sitting isolated will not be willing to share their data, when they know that everyone else is sharing, they know that basically their data is known, and as a result, even they will share their data. So there will be a suppressed prices for each user, given that others are sharing, and it's just because of the correlation among users. And as a result, even if you are a very high-value user, at the end of the day, you will share your data at a very low price. This is exactly when you think about, is there any hope for us, for example, not to join a social media platform to just like hide your information. And usually for myself, I would say that, okay, whether I join or not, everybody knows everything because there are other people who are sharing their information, right? So you have this in mind that others' information, since they're related to your information, will reveal yours as well. And the more on top of that, there are, you can actually show that under some conditions, shutting down the whole data market. So considering the positive effect and negative effect, sometimes it is the whole surplus will be negative, not just socially optimal, but the whole surplus will be negative, less than zero. As if you didn't have any data market, it would be better. So this is not to say that the data markets are not useful. This is talking about we need to have right regulations, and it's necessary to act on that really quickly to make sure that no catastrophic data leakage will happen again. And let me just jump from this. So this, even if you add the competition, things will not get better. And in fact, it may become worse. And the remedy is just by the data sharing, mediated data sharing, which is basically data whitening. We are going to add the correlation scheme where we need to have a trusted third party, and everyone will share their data with this trusted third party. But the good news is that the generated signals by the users, if they share these generated signals and used by the platform, then when a user decides not to share their data, at least their utility stays zero instead of negative. So beforehand, if you have correlation, even if you are not on Facebook, people know about you, right? Because there is a correlation and the data is directly shared, right? But if you at least apply a decorrelation, you can at least guarantee that the person who stays out will stay secure. And on top of that, this was just about like the data and privacy. There are more concerns. So there is a book by Shoshana Zuboff. So if you want to have a Halloween, just read that book. It is The Age of Surveillance Capitalism. So like you will read the first 5-10 pages, said, okay, it's fine. And then you get more scared and scared until the end of the book because it's very real. And it basically talks about the fact that if there is a party that knows more about you than you, then it will have the ability to manipulate what you will. So you would be lured towards something that you didn't want to do at the beginning, and that's called the behavior manipulation. So basically there are, so we were trying to look at it as in a theoretical framework, and basically we showed that it's not always bad news. Sometimes if platform has more information about you, it could benefit you as well, and it could be used to help you, but depends on how fast you will learn that. So if you learn if you learn the state very slowly, then in fact the manipulation is usually against you. So if they have more information, it will be worse for the users. So that's it for today. So there are many other exciting directions that I think are important to be studied at the intersection of data, algorithms, incentives, and society. And if you have any questions, I would be happy to address those questions. Yes.
Wait.
Thank you for the talk. Very nice. Are there any impossibility theorem, like impossibility results in mechanism design for data markets, or is it the same ones as the
impossibility? You mean
like
what?
Like for example, this
open questions or impossibility?
This in normal mechanism design, you have this Gibbard-Thurtwite possibility theorem results for this budget balance and.
Yeah, of course. So for example,
so
like
I think most of them will also translate here, or do you also have something additional?
Most of them will be translated here. This is simply like the similar settings. a lot of like the impossibilities are going back to the data sharing. So if you would like to add the data sharing and specifically like questions related to the federated learning,
Yep.
where you would like to, for example, decide about like how, like the Shapley values and how you want to share while it is budget balanced, then you will get impossibility results and also like computational complexity issues with calculations of the scheme.
Yep. Tommaso.
Thank you so much for your intervention. I'm Tommaso from the University of Pisa. I'm a little bit concerned about the increased use of AI in the recent years. And I would like to know your opinion about the data sharing and if you think that the progress in Europe related to the security and trust on the data could be a solution or a problem for development.
So if you ask me, I'm very paranoid and I'm very concerned, but I'm not the right person. So I think that in Europe they acted much faster than the US. Even when I come here, like every page that I open, I have to do a lot of accepts and change the cookies because they do not let me. So I think they did the right decision. The data was something that was supposed to be. So I was talking with one of the students here. So basically, what the main issue with the data is that you shared it, they own it forever, and you have no idea how they use it. So of course, like the concern that I have relates to what would be the future usage of my data and what would be the consequence cost of that for me. So at the beginning, if it is just there to just like, for example, show me chocolate, it would be fine. But then if they are going to learn that if I like this chocolate, then I will, for example, vote for this party or that party, then I would be concerned, right? So I completely agree with the concerns, and I think that the regulation is a must, and there should be investment. Unfortunately, the direction of the like the investment by the companies are not the opposite, because if you regulate more, there will be less way of like personalization and targeting, which is the main source of the revenue. In fact, for the third-party cookie, like there is like this first-degree cookies that you can like, for example, like if like you were using a browser, they were sharing that they could buy, like the other parties could buy that, and there were a discussion on whether this should be allowed or not. And it was a lost battle. So there are actually, for that one, there are reasons to think that it might, there are some, like, it's not always good to ban or include. So for example, for that one, what could be shown was that, and we have a paper on that, which basically if you completely ban it, what would be, who would be harmed would be the, like the smaller players in the, like for example, like smaller businesses would be harmed the most, and those are the buyers of the data because they cannot gather the data. So as a result, like there should be nice way of thinking about the problem, not 0-1, so that they can actually like address all the aspects. But I agree with you that there should be a very like strong regulation on everything.
And your last question? Yep.
Thanks. I was wondering how far we can assume a rational actor on the user side of such an example of a platform. Because, I mean, if I'm asked to judge the value of my own privacy on a scale of 1 to 5, that will depend on the day probably, depend on how I'm feeling or what article I've read yesterday. So what about that assumption?
Very good question. So even if you ask them 1 to 5, they don't know what is 1 to 5, right? So they are trying to do in different way of scaling. So I didn't put it in the slides here, but they are basically showing you like options that are more meaningful to the people when they want to do the 1 to 5. So just to put a number on it. they were writing sentences that are more meaningful to the people, and they were selecting among the choices. They were trying to like discretize it instead of like asking to just put some number between 0 and 1. They were giving you, for example, 3 options, and that was helpful for people to just come up with the better way of like selecting. But having said that, there was a study by the MIT people, I think in 2003 or so, and they were actually running an experiment on the MIT students to see how much they value their privacy and whether they know what's their value for the privacy. And the way they were like doing that was that like the money that they were putting for the privacy at that time was Bitcoin, which was very cheap, and now all those students are rich. But basically what they saw was that I think basically the same person's opinion was completely would change at the end of the experiment. So basically, even the people who thought they knew, they didn't know what was their value for the privacy. So it's a very valid question. So it's again, that's something that the people should think of how they want to define. And as I said, again, the privacy is defined as the consequences that your sharing data will have for you. So for example, whether it's the price discrimination, which is basically it will cost you more, or whether it's like increased in the insurance, or whether it's becoming upset because you are seeing that, for example, Facebook is like putting like a mark for you under like hidden somewhere in your profile that what is your political party. So there will be a cost for you, right? And based on the application of your data, that cost would be different, right? So each sort of learning algorithm that they will run, it will have a different result, which will affect you in a different way. So as a result, the cost will change over time for the people, and I agree, there will be, it's important to define like a better like covering definition for the privacy.
So just to conclude, maybe I can ask questions, not to you, to all. So based on what we learned, imagine that a startup offers you to buy your power consumption data, and then the startup provides some services to, I don't know, aggregator or DSO or local operator. Are you going to share? Are you going to sell your data? What kind of privacy you will put on your power consumption data? So I think this kind of questions, it might be interesting for us to answer. Good. Please let me join me to say thank to Azarakhsh for wonderful talk.
Thank you. Thank you.